Well, hello everybody, and thanks for joining us. Welcome. My name is Jeremy Whittingham, Head of Community and Content for Advanced Engineering. I'm delighted to welcome you to the third in our series of webinars hosted by Advanced Engineering that we are calling Advanced Engineering Talks, or AE Talks for short. Today's webinar is co-hosted by Dr. Mark-Paul Buckingham, who is the Managing Director of Xi Engineering Consultants. As you probably know, the title is Digital Twins for Accelerated Product Development. And just a word to say about these talks. We're carrying on with the series of them. They're going really well. We're getting a lot of popularity and interest from them. So we'll be continuing to schedule them and do keep in touch on subjects and speakers that we'll be bringing through. And we'll be keeping you updated on that. And it's all very much important to us to, get the community to continue liaising and working together, especially at these difficult times. And we want to bring everybody together as best we can to exchange ideas and innovations. So we'll keep you up to speed on those webinars as we carry on scheduling them. We're also, by the way, open to any suggestions you have for subjects and topics on these webinars. And if you're even interested in perhaps doing one with us, do get in touch with me on that. Be interested to talk to you. Onto our session, a little bit of information about it and what it covers. So digital twins for accelerated product development. By combining the real and virtual world, we can assess products in much greater detail and gather a greater understanding. Historically, a product was only measured before it left the factory and if it returned broken after use. Today, we can continuously collect data to improve our understanding of its usage, optimize its requirements for maintenance, and improve future product generations. Combining this with a virtual version or digital twin allows rapid development in an accelerating world. Now, Xi Engineering, of course, helps clients to accelerate their research and development, solving complex engineering problems by applying advanced multiphysics simulation and measurement techniques. And this, of course, is really where Mark-Paul's expertise lies. Before I hand over to Mark-Paul, a couple of housekeeping issues just to outline how things work. There's a chat function, which you should probably see on the right-hand panel, which should be on your screen, and you can post general questions and comments there. It's open and visible to everybody, and it may well be picked up by Mark-Paul as he speaks when he sees your question. We do, in any case, have a roundup at the end, and speakers can see what you're putting up there. So we might do a bit of a roundup after the end of the presentation too. We do have some polls as well. I think 5 or 6 questions, which we'll be bringing up as we go along. And so please, be great for you to interact with us. I do encourage you to use those. And finally, just a little thing, I think there's a ping that sometimes comes up when these things come up, like questions and polls and things. So I would ask if you could try and keep the volume down on your side to avoid hundreds of pings going on. I think that's it, really. So delighted to welcome Dr. Mark-Paul Buckingham. And Mark-Paul, over to you.
Thank you, Jeremy, for the lovely introduction. And welcome to the webinar. I do hope you find it interesting. Hello to those of you I don't know. As Jeremy said, feel free to ask questions. We'll try and sort of mix them in as we go along. We'll see how that works. But I've got a few polls so that I understand who I'm speaking to and get a bit of feedback about you. So I'm just going to try and share my screen to make sure this works. There we go. So here's my presentation. I'm going to cover digital twins, specifically their use in product development, but them generically as well. So I will crack on. So this isn't a flippant phrase. Obviously, I don't have a DeLorean capable of time travel. But I'm very fortunate in my role that I do get to work on and develop improvements of tomorrow's technologies. Whilst I can't discuss all of them due to confidentiality, I'm going to share a few of them with you today but what I can confirm is tomorrow's technology is pretty cool. I don't normally let people know what I'm about to discuss, but as we are via webinar opposed to being able to see the whites of your eyes in the audience, I thought it might be helpful to see the topics I'm going to cover here. If you've logged on for something completely different, this would be the time to shy off, but I hope you are here to listen to Digital Twin. So that I can give the best possible webinar, I'd like to know a little bit more about you. So we're going to just do the first couple of polls to see where we sit, who we've got in the audience, and then I'll try and focus it around that. So Jeremy, could you bring up our first poll? Please get involved. Let's see if this works. So my first poll there is basically I'm trying to get an understanding to see if you're very technically orientated or commercially orientated or in marketing or some other. So if you could submit a vote, we will see who we have in the audience. Jeremy's just put up the following question. So for those of you that are technical, apologies to anyone that's picked commercial or marketing or other, what a technical activity best represents the work you do. So we have simulation, measurement, software, systems engineering, general product development, manufacturing related or other. So if you could please submit votes for both of those, then I'll know who's on the line. How do we close this off, Jeremy?
Great. Thanks, Mark-Paul. Can you see on your side the figures of the poll?
No,
basically, on poll number one, yeah, people have been interacting quite nicely here. So we actually have just over 68% technical, 18% commercial, and 5% marketing with 10% other. So 66% now technical. So that's a majority on the technical side, followed by commercial, about 20%.
Okay.
And on the second part of that question, if you answered technical, what activity best represents the work you do? The top one is simulation, about 24%, closely followed by manufacturing related, that's 22%. Then we have systems engineering and general product development as the next ones at about 14%.
Excellent. Thank you very much, Jeremy. Apologies, I am unable to see the results, but so we have a good mix across this. So I'll try and deliver this presentation so that it all makes sense.
Great.
So for those of you that don't know Xi, just a bit of background. We're specialists, as Jeremy had said, at combining both real and virtual worlds through combining exacting simulation with measurement. We're one of about 70 globally console certified consultants. So in a minority of expert users. We use a multitude of software packages, but our core that we use is Console. The reason being you can effectively lift the lid on it to understand what algorithms it's using, and if it's doesn't have pre-programmed ones, we can actually write our own code. So for us, it's less of a black box, and it means we can really build simulations that are customized to our client projects. In short, we help speed up technical development and solve engineering challenges by providing an increased product understanding or accelerating the development. Console is a true multi-physics platform. As the name suggests, it can deal with multiple physics simultaneously. Traditionally, some other software platforms were quite specific, so they would just do, say, FEA or CFD or thermal analysis, so which would let you solve one of these. But as this industry has grown, a lot of these are either being combined to produce similar to a pure multi-physics, and let you actually solve these different disciplines simultaneously. So if we can put the next poll, I'm just trying to get an understanding of what sort of simulations you guys get up to. So could you put the next poll up, Jeremy?
Okay, 1 second, here we go, and publishing now.
So does your organization use computer simulation? Yes, no, or not entirely sure?
Okay, that's overwhelmingly yes, 80% so far, just changing, but it's looking about 80% are saying yes to the answer there.
Excellent. That's very good news for all of you. Can we go on to the next question? Sorry, I don't have a myriad of polls. I just really want to get an understanding of who we are and what we do.
Okay. Okay, I'm publishing the next one. Hopefully that's coming up now. So
as 80% of you are using simulation, do you use, so as I've described, the sort of fairly traditional single packages for sort of FEA, CFD? Do you use multiphysics software, or do you combine them all together? Do you outsource your simulation needs, or none of these because you live in the 19th century?
Just having a look now. It's looking like about 50% now are saying the first option on we use physics specific standalone packages such as FEA and CFD, followed by the next one would be we use true multiphysics simulations. That's probably about 20%, but the winner there is the first option on FEA and CFD.
Okay, which is, as I said, a fairly traditional approach. A lot of the different packages
right.
do very specific types of simulation, albeit the market itself is moving towards integrated multiphysics. So a lot of these packages can speak to each other, so you can get a really good understanding of the simulations or the digital twin you're producing. Like I say, we do have some of those packages as well. And we often merge different systems. Console's got a capability of dealing with MATLAB, as several of them do, so that you can do a really holistic model of your system. Thank you for answering those. Did anyone answer they live in the 19th century?
Actually, yes, there were a few of those.
There we go.
18%, in fact. Actually, that's more than I thought.
Okay, let's bring you into the 21st century, or at least give you a bit of understanding.
Yeah. Right.
So, according to the wisdom of the internet, the term digital twin was first used at the Society of Manufacturing conference held in Troy, Michigan back in 2002. So we're sort of 18 years old since it was born. It's attributed to Dr. Michael Grieve, for those of you who would like to know. But before we go all digital, I just wanted to think about the twin bit. So looking at the definitions in the Oxford and the Cambridge dictionaries, a twin is either of two children or animals born at the same mother on the same occasion, two similar things that are a pair, a person or thing that is exactly like another. So obviously a few different definitions for twin. You might recognize the twins on the right hand side of your screen there as the Winklevoss twins. They were the apparent originators of Facebook. And for those of you who are interested, they settled for $65 million when suing Facebook in 2004. Apparently the current market cap is about 805 billion. That's over to you. But the other picture is actually of my brothers, who I found out when preparing this presentation are dizygotic twins. But for you and me, that's non-identical. So the point here is twins have a few different definitions. Let's get all digital now. So like the definition of twin, the definition of digital twin, there are a myriad of different definitions. As you can all read, I think I'll let you read each of these definitions. I just picked a few on the old interweb there. One from IBM. You might not recognize the picture in the middle, but it's Dr. Michael Greaves himself, and from NASA. So I've got a poll to see which one of those three, and I'll give you a little time to read it. I think this might be my last poll, so or maybe I'm keeping you awake later on. Which of those do you think you feel is most accurate when it comes to describing a digital twin?
Okay, I've just put that one up. I think it should be coming up now. Okay. Let me just see how that's getting on. Okay, right. So the winner at the moment seems to be IBM at 58%, followed by Dr. Michael Greaves at 20%. And then NASA
get quite specific about vehicles, obviously, but there are, and if you go online, there are a lot of definitions. So I tried to produce my own definition, which is here, and I had to think long and hard about it. For me, the fundamentals are it's real world data combined with a virtual model of your system or twin. It clearly has to be grounded in the real world, but I'm not so, I don't believe it has to be real time. Obviously, there are benefits of doing it in real time, but fundamentally, it has to be calibrated against the real world. Depending on what you read, there are different subtypes of digital twin, things such as digital twin prototype, DTP, digital twin instance, DTI, digital twins aggregate, DTA. But I think the true question you should ask yourselves is, what benefits do I want from a digital twin? And this, at the beginning of building one, will help you answer a lot of questions. But how did we get here? And why has it taken so long to have what is classed as a digital twin? One of the main drivers is the Internet of Things. Real world data is now becoming so much easier to get hold of, both in commercial and consumer spaces. Your phone, you'll all have one probably, can be used for any number of applications. Recently, phones have, this is actually Android, are trying to collect seismic data from across the globe so that in future they could warn people of earthquakes. A recent study that I saw only this week apparently developed an algorithm for your phone which was 93% accurate in determining if you were drunk or not because of the way you were walking. So we can gather data from anywhere, from anything, and this allows us to actually calibrate the models and feed back into the digital twins. So the second reason, but predominantly this is kind of the first as well, is that of Moore's law. I'm sure most of you know, in terms of computing power, doubling roughly every 2 years. I've got a nice plot of it there. But computing power is such, it's low cost, it's accessible, that we can use it to do innumerable calculations. And we need to exploit this. And this is obviously low cost computing is why we can have sensors out there in the world. So if we look back to how products used to be made, I thought I would use a Model T Ford here as a help define the manufacturing process as we know it today. You would only really know about your product when it went through quality testing just before it left manufacturing. It would then go out into its operational life, and until it came back for either a service or broken, you wouldn't understand anything that had happened within that period, or have very little understanding. Obviously, the Model T Ford produced from 1908 to 1927. Some more pop trivia for you. But really, this sort of highlights where we came from in the early days of manufacturing, and now I'll move to where we live now. So I'm sure you can all recognize this the world's most valuable car company currently, I believe, Tesla. So as we go through manufacturing, we're already collecting lots and lots of data. The car itself is covered in sensors. Tesla are well known for the fact that they have a digital twin for every one of their vehicles. So they have the capability to understand how people use a product, whereas before, as engineers, would have to assume what a user would do. And from experience of launching products on the marketplace, it is amazing what customers do with products. So you get all that real world data, taking away assumption, and it's able to solve and improve performance throughout its operational life, obviously coming to the end of life there. Sadly, cars still crash. So I've got a little diagram here that I prepared that I talk about how we get involved, you know, as I with these things. But you've got measurements in the real world. This is Internet of Things. This is getting the right sensors so that you can feed it into your virtual world. And then once you've got a virtual system, you can actually test it and trial it. You can improve the engineering design, going through these optimization cycles. You can feed that back through to future developments, you know, and again, measure and push this through. This all leads to being able to really accelerate product development. I'm going to cover a few examples of this on specifics, but, you know, whether it be thermal, electromagnetics, these are all the points. I mean, biological systems as well are being run in digital twins, chemical systems, and combining. So we do quite a lot of stuff on batteries and electric motors. So all of these systems, you can create a full virtual prototype that is calibrated against the real world. Listing the benefits of digital twins is actually quite difficult. I put a few down here, but it really is limitless, and you know, it's based on your imagination. You do need to put the right sensors in there so you can get the appropriate feedback, but you can obviously reduce operational costs. You can diagnose and fix, just like the Tesla. If the doors are rattling on a Tesla, it can increase the door locking power so that it stops it. You can obviously predictive maintenance and operation. You can ensure all your processes are much slicker, so that you're not doing getting a maintenance regime that is time-based. You're doing it based on when the system needs it. So many of our clients simply find product development takes, you know, the use of a digital twin and a calibrated digital twin. It reduces the time to market. It reduces the number of physical prototypes needed, because you can build virtual prototypes as well as real world prototypes, just less of the real world, which gets you there significantly cheaper and quicker. Another area in which the digital twin really helps is actually getting a true understanding of the product. Obviously, the sensors you deploy are limited. You know, you can't put sensors over every little aspect, but a virtual model with underlying physics can let you determine how things are working and also solve some of these issues. So quite commonly, we build a very complex virtual model, and then we look at sensitivities, and then that allows us to actually build a more refined model. We then refine it down, but really understanding why things happen and why we're getting the sensor output that we do. When you build the digital twin, as I said, you've got to think about what you want from it. This area here, we quite often find there are sort of three drivers to the models that we'll use. So one is obviously future product design and development. which is should be hopefully self-explanatory. But actually getting product understanding during its operation, so that continuous data or buffered data, like I said, I'm not wedded to real world as long as you're collecting good data and you can timestamp and and quantify it, then that will work. So it'll help you as engineers, as people with products in the market, understand what happens to it, how it's treated, how it works. And then another side of this is for your client, looking at operations management, maintenance, and so on. You can feed that in. So depending, you can have a core that works for all of this, but different interfaces to different simulations to allow people to get better benefit from it. It's often how we build these systems. So I've got a few examples here, all quite varied. Like I say, I get to see lots of weird but predominantly wonderful technologies. So this first one here is a high-end headphone produced by Warwick Acoustics. I didn't know when we started this project that there's a market for headphones between £10,000 and £30,000, but there is. This is for high-end audiophiles or sound professionals. During lockdown, this is quite prevalent. If you wanted to set up sound recording or sound reproduction at home, you could either spend somewhere in the region of £100,000–200,000 setting a room acoustics up, or you could buy a pair of headphones such as this. But what Warwick were doing was developing a novel electrostatic speaker. This had lots and lots of variables, including the film thickness. Apologies, I live near the airport, so you're about to hear a plane go past. It had film thickness, the geometry, the tension in the film, the geometric spacing. There's several sandwich layers here, so a meshing and mesh diameter. So lots and lots of variables to optimize. They were going through a process where they did traditional prototyping. It was taking them sort of 2 weeks to get a prototype built, tested, and analyzed. And we came in and said, look, let's stop doing quite so many prototypes. And we built effectively a virtual twin calibrated to all their real world measurement. And we were able to put a prototype spin in a virtual prototyping within an hour. So we ran prototypes for actually a couple of months trying to optimize all these different variables. And when they launched this product on the market, which was their first ever product, they won all of the awards that you can see on the screen there. It really did. We managed to get the price point in at £5,000, so half the price of what would be deemed the lower end of the market, but it actually beat them for quality. And their managing director, if you look at our website, you can see the exact quotes. But for him, we got to market cheaper and faster, which is what a lot of us doing in the product development. We've since done a second headphone for them, which again has won lots of awards. But ultimately, we're taking this with them into the automotive sector because these systems, I think it's about 28 grams, the speaker or the driver from this, whereas your an appropriate, standard speaker would be in the region of 250 to 500 grams, so half a kilo. And when you have 8 in a car, it's a significant weight reduction and efficiency, plus the audio quality is better. Have we got any questions coming in, Jeremy, just to check whilst we're going along?
Yes, actually, I'm going to pick up one or two. We can look at the questions tab as well, Mark-Paul. Our friend Ian Gardner put in a question: can the twin be purely a process? If you can see that one.
Yes, a twin could be a process. I mean, it can be anything that happens in the real world. So in some areas, a digital twin can be used to solve problems that you just couldn't do through either, moral or scale. If you're looking at, sort of medical applications, say heart valves, etc., you can test them and run them and get some real world data and then use a digital twin to assess the viability. Or for large-scale activities of humans. Obviously, COVID, that's been modeled quite heavily. You just wouldn't be able to run tests on that scale. But yes, a digital can be the full process. It can be your manufacturing process. It can be, as I've said, biological. Literally, we have the computing power to be able to recreate these things in a virtual world and test them.
Great, and I think that relates as well to a question from Bradley York Biggs. What experience have you had of employing machine learning to inform data with your simulations? That's probably perhaps a related question, is it, Mark-Paul?
Yeah, I kind of cover this in the sort of future, but certainly computer learning, machine learning, and AI in terms of optimization has begun and is going to become more and more prevalent in the front. At the moment, we do optimization from a human basis, as well as doing computer-based optimization solely by itself. And at the moment, we're finding, the optimum sort of sits between the two. But with machine learning and AI, obviously that's going to go one way. Computers can do a lot more equations simultaneously than us humans. But this is why I said and mentioned the black box initially. What you need to have, you don't want a computer system that's rubbish in, rubbish out, the old adage. So trying to understand what that does, but certainly optimizing system processes through machine learning and computing is here, and it's only going to get better. So I've got another of our previous projects. This was actually fairly old, sort of 5 years ago. So, stepping back half a decade. But we were working on the world's largest onshore wind turbine, which at that point was a 210-meter tip height, twice as big as Big Ben, larger than the Gherkin, not as big as the Eiffel Tower, to put it in context, but a huge machine. And we did measurements, so we deployed sensors all the way down the tower, throughout the turbine itself, and then in the far field and near field, because we were looking at the structural dynamics and the associated acoustics. So building a full model of this, and we needed to be able to propagate the high frequency sound waves to a couple of kilometers. So those of you that do know how simulation works, this was a large mess, to put it politely. So we actually, in 2015, had to move this model to the UK Supercomputing Centre in order to be able to get it solved in a reasonable time. Now in 2020, we don't find ourselves having to use the supercomputers. We can use the cloud, and we can literally turn up the power appropriately to be able to get rapid solutions, and even on large-scale devices such as this. But the dynamic structural acoustics, the holistic system, trying to improve this and improve the acoustic outputs. So that was a good fun product. But if you ever do have to go up a wind turbine that's got a nacelle at 140 meters, it does sway a lot. So take your seasickness tablets. Next slide. So I put this one in because it was rather interesting in that the virtual device came before the actual real world device. So in some instances, we find ourselves helping design products where they've literally never been built before. So here we have to lean on, our experience of similar systems. So the drive here was to look at the holistic system. This is a tidal turbine, for those of you that don't recognize it. Sits on the seabed, and the tide goes out, comes back in. There's only a small window of sort of 45 minutes where there's not a really strong current. So this thing needs to have a very long maintenance free period. They were designing for a 5-year maintenance free period. And all the subcomponents were coming from several different suppliers. So the blades, the gearbox, the drivetrain, the nacelle, and the subframe. So we built a holistic model so that we could understand the interactions between it. Obviously, vibration and fatigue and dynamics is certainly going to affect its maintenance regime. But because this had never been built, what we were able to do was go to our experience of other markets and sectors that were similar. So drivetrains on wind turbines, gearboxes on wind turbines, and we were able to scale real world data to give us some confidence in the model. And then as it went through different testing phases, so there was generator, drivetrain, standalone tests, we knew it was going to go through those processes. So when we built the models, we had them set up ready to take that data in. So we worked right through until this product was out there and optimized. We had to do quite a few changes to the structure because of the masses and so on with the dynamics. And since then, we went on to produce another couple of devices for them, working with them with this holistic model that ultimately became a sort of true digital twin, taking the real life data into it. If you haven't heard of it, it's because it's not had major failures like some of the other tidal turbine devices, which obviously, if you go through this sort of process, you reduce technical risk quite significantly. Here's some more amazing technology. If you haven't seen the Ocado robots, go online. It's in the public domain now. But the Ocado technical team have been redefining logistics and delivery services. I think most people used to think of them as a grocery company, but they since split the company in two. So they've got their technology and their groceries. But effectively, the picture there on the right is their grid system. So they have a grid which is about 8 meters high, and they stack boxes on top of each other full with different products. And then you have robots. They have about 2,000 robots running around the top of this, mining the different products to be able to put them into your box and then go through to transportation. They've managed to take the human out of this picking and packing process pretty much fully. At the moment, they only have the driver of the vehicle. So, and we all know where that's going to go. They're doing a lot of work on driverless vehicles to deliver this. But one of their first challenges was, how do we stop machines, 2,000 machines, from hitting each other, which was amazing. So they upscaled air traffic control algorithms by a couple of orders of magnitude. But for them, they understanding this rather huge system, it's they can be sort of 250 meters long and similarly wide. And what we've been doing with them is actually getting real world data out of the grid system and the grid, so that they can understand the lifetime of their products and develop more optimized products going forward. None of the different setups are going to be exactly the same, so they need to be able to have these virtual prototypes and digital twins to understand all the sort of variables and how these systems run as well, because it's not that easy to predict exactly how many loading cycles and so on. So it's measuring that and feeding it back into the twin. But like I say, if you've not seen this tech, go and have a look online. It's great. So looking to the future of the digital twin, I think some of you have asked several questions about this, but we're going to see, a massive uptake in the Internet of Things. Sensors, as I said, computing power has got cheaper. Sensors have got cheaper, and we are now distributing these across our everyday lives and also commercial lives. So we can get access to more data, which means we can make and we can calibrate effectively our virtual models of these systems more frequently and more accurately. We're going to see this both in consumer and in industrial products. It literally is endless. You know, sitting here, I have a myriad of devices around me that are measuring all sorts of weird, wonderful things in order to be, you know, improved for future generations of products, or even updated as we speak. So the complexity of these systems is going to increase massively with, you know, in 2 years' time, we're going to have twice the amount of computing power again. But machine learning, machine optimization, and artificial intelligence is going to really drive, you know, it's going to be the beating heart of a lot of these virtual systems. As I said, at the moment, we do a mix of both, but obviously moving more and more towards the machine learning type of systems. It's, as I think I just mentioned this earlier, it's going to let us assess things that we couldn't do, you know, morally, or, you know, medical devices and this kind of thing, where, you know, we couldn't test them at early stages of clinical development. It allows us to do these sorts of things, or actually large scale, you know, human-based activities and so on, that you just couldn't set up experiments to do. It's phenomenal what is going to be happening. But I think when we started this, 50% of you had single standalone physics and prototypes. You're going to get more and more physics combined, whether it be through different platforms or a single package, and you're going to be getting data in that feedback loop to understand more and more and be able to optimize and make these things more efficient. We live in a world where, you know, efficiency is key. There are finite resources. We hear it daily. Worries about lithium ion in terms of you know, our batteries. For me, it's more about rare earth magnets. We're helping a lot of companies develop novel generator systems without the need for rare earth magnets, which are in very limited supply. So it's these systems and these virtual prototypes that really do let you get there much quicker. We can build front-end interfaces. We often build GUIs. I go back to the headphones that we were developing. We built them a front-end interface, which the whole company could sort of test and say, well, what if we made it out of gold, or what if we made the headphones this big, and it would tell them how good that system was. So, you know, marketing and other people without the sort of technical background could quite easily say, you know, what ifs, and see how these were happening. I seem to have, Microsoft seems to have paused. So really just rounding up, we're going to come to questions soon. I've got a few of our sample publications here. You get Console News, you can get it online, but it's full of brilliant different examples of digital twins and virtual prototypes and systems in the real world that are being used here and now. Our website has examples of all the things I've discussed earlier. So I'm happy. Thank you for listening to this webinar. I hope you found it interesting, even if you just understood twins a bit more. So happy to take any questions for the remaining 10 or so minutes.
Thanks, Mark-Paul. That's great. I was going to actually say, I think you had another couple of potential poll ideas. I don't know if you wanted to put those forward to the audience while we
okay.
were still had a little time as well.
Let's check if you're still awake in there.
Well, let me publish this. This is, does your organization utilize a digital twin in some form or another? But I think, would you like me to publish that to the audience? Let's do it. Okay, here it comes, everyone.
I wish I could see the real world answers straight away. I'd love a bit of data.
Yes, I must admit that's a bit odd with this system, Mark-Paul, and I'm a bit new to it still. So I'm going to try and follow up on how that how we can hopefully perhaps change that if we can.
So the answers are yes, no, and we would really like to in the near future.
Yeah, it's Doing quite nicely. So actually, it's quite equal. So, does your organisation utilise a digital twin in some form or another? Yes, 43%. No, 39%. We would really like to in the near future, about 18%.
Well, just on that, what I would really emphasize is the understanding and learning you can get about products when you've built them in the virtual world is amazing. What we do in the way we build them, I think I mentioned it briefly, was, we'll put in all the variables until we build a really complex model. And then the key is to actually understand the sensitivities to different variables and then boil it back down so that you've got, a real workhorse that can take the data in and crank it quite quickly, having understood those previous sensitivities. So it's, you learn things that you just wouldn't have thought about, even your own product, through applying one of these. And for those of you, obviously, sort of half of the audience are yet to build a digital twin. Hopefully, some of the benefits I described should help. But like I'd said, if what benefits do you want out of a digital twin? Think of that before you start building it. Do you want more customer interface? Do you want to understand your process, your manufacturing process more? Do you want to understand what the consumer does with your product? Do you want to optimize it for its lifetime? Do you want to optimize it for the amount of materials used? All of these questions you need to ask yourself, and then you can make sure you've got the right sensors giving you the right data, and you can build the twin ready to accept this data, even if for now you don't have those sensors in place. Do we have a final poll, or was that the final poll, Jeremy?
We do have a final poll, if you'd like to put that up. I'm putting it up now. Here we go. What best describes your organization's product development process? And there's 3 options there.
So I'm trying not to be flippant or anything, but rapid prototyping is really helpful and really beneficial. But what you need to ask yourself is, do you actually need to build a real world prototype? And can you shorten your time to market by using more virtual prototyping or digital twins to assess it than real world entities? So I've got here prototype, test, repeat, launch, fairly traditional. You may well be doing rapid prototyping. Computer aided engineering, so you're helping design it, optimize it, prototype it, test, repeat, and launch. Or doing a lot more of the virtual prototyping, where you're optimizing it all and actually minimizing the amount of real world physical prototypes. So where does our audience currently sit on that?
Yeah, computer aided engineering is significantly ahead in that, about 50% on that. Then followed pretty equally, probably next by virtual prototype, virtual test. That's probably, I think, about 30%, and then prototype, test, repeat, launch is the lowest one. The rest of it there. Yeah.
Back to my Moore's law point. We've got so much computing power at our beck and call now that virtual models, accuracy is this. It used to be the concern for many. It's like, how accurate is my model going to be? My technical director is always saying, every model's wrong, but what you need it to be is accurate to give you sufficient understanding and confidence in your product. So getting this computing power, setting it, the accuracy and the capability of the different software packages, like I said, we run console quite heavily, is the accuracy and the computing power is phenomenal. And now there is less and less concern. As long as you're calibrating it to the real world or getting some touch zones, you can tell if it's really providing really good output. So I would certainly look at your product development process and see, do I need that many real world prototypes? Can I cut that number down? Can I optimize all these different variables using computer multiphysics or digital twin solutions. So I think we're running out of time now, Jeremy. Thank you all for entering in those polls. I can't wait to see the final results of all of them in a graph format or something. So do you want to pick up a final few questions?
Yes, Mark-Paul. We've had quite a good group of questions. You may be able to see them there.
I can see one. Which application industries machines are you using Console on? We use this literally. One of my taglines is, if it obeys the laws of physics, we can model it. We work in a whole number of industries, so we're very heavily involved in renewable energy. We are heavily involved in electrification of transportation, but we do things such as headphones. We've worked on bagpipes. If you look at our website, we worked with the pandas at Edinburgh Zoo. It appears pandas have a much higher and lower hearing frequency than humans. So the pandas at Edinburgh Zoo were getting disturbed by some building work going on, so much so that their hormone levels were off the roof and could actually cause them to die. So we did a load of simulation and modeling and measurement around that, and designed them a new acoustically optimized for a panda new facility to live in. So literally we get involved in everything weird, wonderful, and complex. Obviously transportation, energy, consumer products, medical devices, ultrasonics, literally everything. We really love a challenge, and because Console is pure multi-physics, I mean, what relates all those industries? I mean, it's physics. We do a lot of dynamics, structural dynamics, acoustics, electromagnetics, thermals, fluid flow. So we really do get involved in lots of these industries. And as I said, Console's capable. There are different versions and different packages to cover all of these. But if we find that it doesn't have quite the computing code within there, we can write our own code and algorithms specifically for our clients. And we can put front ends, we can give you an online GUI so that you don't need to do all the legwork. You can literally have your model and optimize it for yourself and do all the what ifs. Let's look at some other questions.
Yeah, there's an interesting one I saw from Michael Blackburn about 4 minutes ago. When you created the headphones twin for Warwick Acoustics, did you take the CAD data and work from that? When CAD data is not available, how reliable is a digital twin when the nominal sizing is not available and so the item is measured?
So obviously, depending on the different packages, a lot of things are designed in CAD, obviously, and you've got some file types, step files, IGS files that you can translate them across to. Console and some of our other packages have different geometry importers. So we actually look at the geometry to see what it is. And depending on complexity geometries, we can either actually just build our own geometry from scratch, or we can import the full CAD. So this comes down to the point of the level of detail and the complexity you want in it. Often we'll have a more complex geometry and more complex elements, and then through the process we'll whittle that down so you've got a really good tool that is, you know what the sensitivities are, so you can make it that bit simpler. Often clients are going, oh, this is really simple model, why did it take so long? And it's really understanding all the different factors, geometry obviously being one of them, but we quite commonly use different imported step and CAD files. Geometry for the headphones was one of the very specific points, both in the film thickness, the spacers. So we were designing as they were different variants and looking at how this optimized. But that's a really good question. Thank you.
Okay. Well, thanks, Mark-Paul. We're sort of coming to the end of the hour. So thanks for all these other questions as well. We had quite a few, and I've taken note of all of them. So perhaps, Mark-Paul, we can get back to some of the questions afterwards, and go from there.
Happy with some homework. Well,
great.
Thank you all for listening. I hope you got something out of that. You know, for me, I like to see the whites of your eyes, but the polls let me know, a bit about yourself. Have a great day. If you need any additional stuff, I think, Jeremy, you can get in touch, or,
Absolutely. Yes, absolutely. And of course, everyone, you'll get an email after this anyway, with a link to being able to see this again on demand, or for any of your colleagues, if you want to push that over to them to see it on demand. Mark-Paul, anyway, I've taken note of those poll results, so I can send them to you for your reference. It seems the system doesn't show the speaker that, but not to worry, you can see those. So I would like to thank you, Mark-Paul, for everything today. Great insights and walkthroughs. As Mark-Paul says, I hope it's been useful for everybody. We have some really good questions. As I say, these talks, these webinar series, they'll continue after this one, so we'll keep you up to date. I apologize earlier, by the way. I think there was an echo, which we sorted out, but hopefully the quality was generally good. So I hope you've enjoyed it. I think that's pretty much everything from us. So thanks to everybody again, and we'll probably do something in a couple of weeks, but we'll keep you we'll keep you up to speed. Thanks a lot, everybody, and take care. Stay safe. Goodbye.
Thanks very much. Goodbye.